Αν το παρουσιάζει, πηγαίνει από την
Δεν έχω προλάβει να απολύσω. Εδώ κάτι μου σε θέμα.
Δεν τι κάνει. Να κάνουμε ζωντανή, οπότε πρέπει να ξεκινήσουμε. Πολύ ωραία.
Δόξα τα βάλω το λοβεράκι λάθος και βάλω το βολέι. Και για την παρουσία στη σχολεία και για το δόξα. Πρέπει να είσαι σοβαρά εγγύηση. Θα το δώσω αυτό. Παιδιά, δεν πρέπει να κάνεις όταν μετάδοση, ότι λέγεται αυτή τη ζωή του κόσμου. Οπότε δεν τραγουδίστε. Όχι, όχι. Για άλλαξε τραγούδι και θα το πω.
Καλημέρα, θα μου επιτρέψετε να μιλήσω στα αγγλικά. Good morning, dear colleagues, dear students, dear friends and the followers of the Science and Technology Museum, the University of Paleo. We are very happy to have you all here today, and we are also very happy to our guest here, Professor Paul Mason from the Department of Geological Sciences in the University. And most of it, I want to thank him because he gave us this very nice opportunity to find each other again in the theater of the museum, person by person, face by face. It's a very good opportunity. Thank you for this as well. And I will give the floor now to our director, Professor Paul R.D, to give greeting to all of you and our host.
Yeah, Professor Azor, thank you very much for accepting our invitation to give a talk today. And some good to our colleagues, artists, to give us the chance to meet Paul and learn about Emergence. And of course, thanks to the director of the museum, to lead the MCO for the organization of this talk. Paul, I read the abstract of the talk. I'm very curious to see what you do with the study. Okay. Thank you.
Right, I don't want to take too much more of your precious time and Paul's precious time. I just want to say a few words to introduce Paul. Oh yeah, I can take my mask off. I forgot about that. So thank you very much for being here. Paul is first and foremost a very, very good friend, very close friend, and a very close collaborator for many years. We met about 15 years ago, I believe, in the Netherlands, and we've been doing a lot of work together on the early Earth, which is the topic that we will be covering today, or at least part of the evolution of the early Earth. And we really truly look forward to this talk, which was actually published recently, and the paper in Nature Science, a high profile study, which is available, of course, to anyone who would like to read it. All I would like to say, and just a few words about his biography. He comes from England. He grew up in Yorkshire. He studied geology at Durham University, and then he moved to London, where he did his PhD and subsequently postdoc work. And for about 25 years now, he's been in Utrecht as an academic, 5 years, the last 5 as a professor in geology. He does a lot of hydrology, he does a lot of geochem, he has a lot of diverse interests. But one of them, and the one that brought us together, if you like, is his love for the Earth, for the Archean, for the evolution of our planet. And that's exactly what we're going to be talking about today. So I don't want to take any more of this time. I want to make him available to you. So Paul, thank you very much for coming. We really look forward to it. And so with you.
Thank you very much for inviting me to come here. I'm absolutely delighted to be here in Patras for the first time. And it's the first time I've actually left the Netherlands for 2 years. So I saw the mountains last night for the first time, because the Netherlands is very flat, as you know. And I was really excited in the car driving from the airport to come over here yesterday. I was looking out the window, taking photographs, telling Harry how much I miss being in the mountains. This photograph here, to open my talk, was taken in 2019. We were in the Barberton Greenstone Belt in South Africa. And the hillside in the centre here is a place we were working at the time, looking at some of the rocks which I'm going to describe to you today. This is a very remote place, actually. It looks very calm and pastoral, but actually people don't go here. So we were the first geologists to go here in about 45 years. So back in the 1960s, there was lots of mining done in this hill. The nearest road is over the back of that mountain. And we went here every day for about 10 days. It took 3 hours to get to this site. 1.5 hours in a vehicle, driving along forest tracks, and then 1.5 hours hiking. And you might wonder, why didn't we camp in this place? Why didn't we stay there? Well, this hillside is also home to lots of monkeys and baboons, and some of the most poisonous snakes that you find in the world. Mozambique spitting cobras, mambas. So it's not a very safe place to stay. I like to show this photograph because this is how we used to work as geologists, and now we're beginning to go out again into the open world. This is the first time that you've all come together as a department today. I understand that's very nice. So I'm going to talk to you today about a scientific problem that has puzzled many people for a long time. And that's how to show when the first land appeared above sea level. In my title, I talk about felsic crust. I'm going to explain today what that means and how we can trace it. But on the left-hand side of the slide here, we have a photograph of the Earth as it is today. And of course we know that because of plate tectonics, the Earth's surface has changed dramatically over geological history. And as we go back in time, we have less and less felsic crust, we have less and less continental crust, and less land. And it's puzzled scientists for many years how much land did we have back at the beginning of Earth's history. When did it first appear? We know we've had oceans on the planet from about 4.4 billion years ago. We can see that by looking at ancient fragments of zircon crystals. I'll show you more about that in a minute. So the Earth probably started as a water world that was completely covered with oceans. And then at some point, the first land masses started to appear. This is an estimate from a paper by Ilya Binderman from 2017, where they used oxygen isotopes in ancient rocks to try and calculate the amount of crust. And they estimated that the Earth was a water world until around 2.5 billion years ago. So that's in the Proterozoic. And what we've done in our work is push that date back by about 1 billion years. I'm going to show you today how we did that. Now, before we go further, you will probably ask the question, why does it matter? Why do we care if we have land above sea level at this period of time? Well, there's some very good reasons for that. And I'm going to show that quickly here on this cartoon. So, at the top of the slide, you see it says exposed crust strongly influences biogeochemical cycle. So what does that mean? When we have land above sea level, that land weathers, it breaks down, and sediment gets carried in rivers into the oceans. And that sediment load carries with it nutrients which get delivered to seawater. And some of these nutrients are of key importance for life. This happens today. Phosphorus and iron gets carried into the oceans, and it fertilizes the oceans, and it enables life to thrive there. There's another reason why this weathering process is important, because it draws down CO2 from the atmosphere, and that regulates climate. And this is a key issue that many people are studying today. The main exit route for carbon dioxide from the atmosphere is through weathering. It's a very slow process. It takes hundreds of thousands to millions of years, and that's the main reason why we're so worried about climate change right now, because to address the balance, we need this weathering process to kick in. And this is also important on the early Earth, because as soon as you have exposed land, you can remove CO2 from the atmosphere and it changes the temperature of the planet. And then finally, if we have land, we create a whole set of environments, like shallow marine environments, shelf environments, beach environments, and so on, which sedimentologists like to study, of course. And these are places, again, where early life could have developed and thrived, because you can bring bacteria, microorganisms into contact with nutrients and sunlight. So there's many reasons for studying this. Of course, we also have on the seafloor oceanic crust, basaltic crust, mafic crust, and that also delivers chemical constituents to seawater, but it doesn't happen at the same speed, at the same rate as where the continents are interacting with seawater. So it's a very nice question to ask. Can we see land up here? And these are all the scientific reasons for wanting to know that. So let's go and have a look at the geological timescale and try and figure out what we know from the geological record. So on the left-hand side of the slide here, I've got the whole of the geological timescale. And you probably don't look at this very often because many of us work on Phanerozoic, and we look at rocks which are only a few tens of millions of years old. But when you look at the whole timescale, we go back, of course, to 4.5 billion years ago in the Hadean. And the oldest material that we can find on Earth are zircon crystals, which I mentioned a moment ago. They look a little bit like this. I don't know if you're familiar with this, but the oldest material we've ever found on Earth comes from a place called Jack Hills in Australia. So these zircon crystals have this chemical formula. It's a zircon silicate mineral. It's very resistant to weathering. Zircon doesn't break down easily. So these fragments of crystal material have been preserved ever since the Hadean. We don't find any complete rocks from this age, but these zircons would have been produced in a felsic igneous rock. So you can't make zircon in a basalt, but you can make zircon in a granite. So their very existence tells us that we had processes in the Hadean which produced rocks that look like granite and look like crusts that we have today, continental crusts that we have today. So this is a big clue that continental crust started to form very, very early. But the total number of zircons that we have is rather limited. We have a few tens of these zircons, maybe a few hundreds even by now, because we're finding them all the time, finding more of them. We've looked at oxygen isotopes in these zircons, and those oxygen isotopes tell us that we had liquid water at the Earth's surface at this point. So that's why we know we had oceans. So we had oceans around 4.1 to 4.4 billion years ago. So let's go forward a little bit. The oldest rocks that we find are from Canada, the Castor gneisses. And these are essentially bits of lower crust. So they're highly metamorphosed rocks that look like the lower crust today. And their existence, again, gives us a clue that we're making crust at that time. But these rocks are rather mafic in composition, and they don't tell us very much about what would have been exposed at the sea level. For that, we have to jump forward even further. If we go to a place called the Pilbara Block in northwestern Australia, we can find rocks which look like they were exposed at the surface. We find what we call Paleo Salts. So these are actually fossil soils. So here we've had rock in contact with the atmosphere and the water, and it's been weathered. And we can date that weathering process back to the Archean. This is actually quite difficult to do, because of course weathering can happen at any time between when the rocks formed and when we find it today. So we have to prove that the weathering process happened billions of years ago. And that makes these paleosalts quite controversial. And several of my colleagues would say this is not a paleosalt from the Panorama Formation. This is the oldest one we think we've found, but it's controversial. It's difficult to study this. So what you can see here is that we're trying to solve a big question with different types of evidence, and these different pieces of evidence don't necessarily answer that question. Despite that, Earth scientists have made all kinds of models to show how and when the continental crust formed. And this is an overview from a review by Yun Korinaga. And actually, Yun Korinaga is going to give a talk online this afternoon. If you Google his name, you can find it. You can go and listen to it if you're interested. There's a whole series of symposia about archaean geology, which is freely accessible. Anyway, he wrote a review paper. So here we have time on the x-axis, and here we have the amount of crust normalized to the present day, value of 1. And these are all the different models which are published in the literature. It's different colours. The blue colours down at the bottom were made by geologists looking at modern day rocks, dating them, and then trying to work out from the age of rocks what appeared when. And this is a study from Hurley and Rand from 1969, that's why it says HR 69. And Hurley and Rand went to the North American continent, they took all of the age data that they could find, and then they tried to recalculate how quickly the crust would grow. And that didn't really work very well, because they only looked at North America, and they only had certain ages available, certain data available at that time, and that's why it deviates strongly from all these other records. If you look at the other extreme, we have, for example, A81, that's Armstrong from 1981. These curves are constructed from what we can see in the mantle, mainly. So we can go look at mantle rocks, and we can figure out when melts were extracted from the mantle over time, and then we can calculate how quickly we think the crust grew. And then in the middle, we have lots of yellow and green curves, and these are calculated mainly today by looking at the Zircon record. So you can put together all the Zircon ages that have ever been made in labs all over the world, and then try and reconstruct how quickly we think the crust is growing. Now, what does this diagram tell us? It tells us that everything is possible, right? It doesn't really give us an answer. So different people with different models, different types of data have found different things. So if you go back to the early part of Earth's history, we have a huge range in the amount of crust which was present from a small fraction up to even more than the present day. So it's a very controversial issue. So what did we do in our work? Well, what we've done is look at the chemistry of seawater, because that's linked to weathering. And as crust emerges above sea level, we start to introduce components into seawater from that weathering process. And what we've done is focus on a very old isotope system that's been studied for many years, 60, 70 years. That's the rubidium-strontium isotope system. This is one of the first radiogenic isotope systems that geochemists ever looked at. And I want to spend a bit of time explaining it now, clearly to you, so you can understand the rest of my talk. So I'll go slowly again. So what we have is we have an isotope of rubidium-87, which can undergo radioactive decay to form strontium-87. And the half-life of this process is 48.8 billion years. So extremely long, way longer than the age of the Earth. So that means that the rubidium which was formed during the formation of our solar system is still undergoing radioactive decay today. This is such a slow process. But actually quite a large proportion of that rubidium has already decayed. And it forms an unusual isotope, a rare isotope of strontium, strontium-87. Strontium-87 wasn't produced in large amounts during nuclear synthesis during the formation of the solar system. So when we find strontium-87, we know it's formed from the product of this process. Now, some of you might know about this already. This is from a textbook by White from 2013, and it shows how the strontium isotope system works through time. So again, we've got a very long time axis here, 4 billion years, 4.5 billion years. And this is what happens to a strontium isotope over time, strontium isotope ratio. So here's our 87 isotope, which is produced from the rubidium. And what we do is we divide Now here's the starting point for the Earth. We have a strontium 87 to strontium 86 ratio, which is initially set by what we see in the solar system when it's created. There's actually some strontium 87 that's already there. And then that ratio changes as we grow in more and more of the radioactive isotope. And this is what would happen for the whole Earth through time, the whole curve. It's a very small difference. You can see on this x-axis, on this y-axis here, that we're moving a few decimal places and a third decimal place. So it very gradually changes. Now the trick here is that the ratio change is going to be greater if we have more rubidium-87 around. Now during melting and crystallization in the crust, our felsic crust tends to concentrate rubidium. This is a phenomenon that's related to the incompatibility of rubidium. So in your petrology classes, you've maybe learnt about this. Different elements have different incompatibilities. And the crust, the continental crust, tends to be enriched in certain elements. And rubidium is one of them. We have a lot more rubidium in the continental crust than we have in the mafic crust, which underlies the seafloor. So because we have more rubidium here, we grow in more strontium-87 in the continental crust. And that's represented by this line here. And the mantle has rubidium extracted from it. So the mantle also grows in more rubidium, more strontium-87 through time, but it does it less slowly than the crust. So this is the mantle evolution line, this is the crust evolution line. And the more felsic the crust, the steeper this line. If you have a mafic crust, it's going to be a much shallower line somewhere in the middle here. So the message from this diagram is that everything's changing, but some things are changing more than others. And what we have here is a tracer for continental material, because the continental crust changes the most. So our continental crust weathers. That weathering process carries more strontium-87 into seawater. And strontium is a very soluble element. It's soluble in fluids, so it gets carried and retained in seawater. And you might be familiar with the fact that we use strontium isotopes and phanerozoics sometimes to date rocks. So some of the carbonates from the mountains here are measured for their strontium isotope composition, and it's actually used to give an age, because we know how the ocean changes through time. I hope that's clear for you, because this is the basis of what I want to talk about next. We've known about this for a long time, and curves have been created for how seawater changes through time and linked to how crust would grow through time, and it's traditionally been done with carbonate rocks. Carbonate contains a lot of strontium, precipitates from seawater, so we can use this information to reconstruct how the crust would grow through time. This is a review article from Chris Hawksworth from 2020. It's a very nice paper if you want to go and read more about this. And there's lots of information on this diagram. I want to focus on the blue line quickly. That's strontium isotopes in seawater. And this is how that curve has changed through time. So this has been plotted by measuring lots and lots of carbonate rocks which are directly precipitated from seawater. And you'll see when you go back in time, the ratio drops, and that's exactly what you would expect based on what I just told you. We have less of the decay product from this radioactive decay process in seawater as we go back through time. It's not a straight line, and it's not a straight line because the continents are rising and disappearing again above sea level as we go through time. So people have used this to make the purple curve, which is the amount of continental crust. So this is a model calculated from what the isotopes are doing. I don't want to go into too much detail about how that works right now. But what I do want to show you is that when you go back down here, this diagram becomes very messy. So we're 3 billion years here, that's the age of the rocks, and we've got lots of different estimates. There's lots of dotted lines there and letters, and there's a very good reason for that. And that's because the carbonate record doesn't really work very well when we go back very far in time. So to understand that a little bit better, I want to talk about what these old rocks actually are. We have a limited number of places in the world where we can study Archean rocks that are windows to the past. I mentioned already in my talk, I go to South Africa quite regularly, and that's actually one of the reasons that I started working with Paleo very closely. We've worked in the Carpal Craton here in Southern Africa. And I already mentioned the Pilbara Craton in Australia today. What's the best places to study Archean rocks from the Southern Hemisphere? It's very nice to geologists to go to these places, visit these countries, go to these beautiful places in the world. In Europe, we don't have any of these very old rocks. The closest place you can go is the Kola Peninsula in Russia. So what do we need in order to reconstruct seawater, reconstruct the emergence of crust? We need rocks which are sensitive to that process, so they have to record the process somehow, accurately, and with sufficient precision, so that we can see small differences. And to do that, the rocks have to be well preserved. Now, this is a really big issue when you're looking at old rocks. They've been sitting in the crust for billions of years, and a lot of them are just not well preserved. They've been metamorphosed, they've been through tectonic cycles, mountain building cycles, and they're weathered, a lot of them. A lot of the ones that you see today, the Earth's surface, have been interacting with rainwater in recent times. And when we look at old rocks, we also need to be certain we're looking at a global signal. If you want to construct a global emergence of crust, you need to know that you're looking at something that's not locally controlled in a small basin, in a small part of the Earth. And these are all really big challenges for early Earth geologists, early Earth geologists. And the reason that those curves were very poor on the last diagram is shown somewhat here. It's because we're looking at carbonates, and carbonate rocks are not very well preserved during metamorphism, and they're very susceptible to weathering. And this is another diagram from a review paper that came out this month, where they've tried to draw a seawater curve from the carbonate records, and there's a lot of information on this diagram. But what I want you to look at are all these light grey triangles in the background. This is all carbonate data from the early Earth, and somehow you have to make sense out of that. Now, generally speaking, when rocks are altered, you increase the strontium isotope ratio. And that's because in the crust today, we have high strontium isotope values. So when any weathering happens, you tend to increase these values. So what they did in this study is they took the lowest values from each of these data sets to reconstruct the seawater curve. But when you get down here, it gets very, very messy. In this review, they actually used our new data, and I've blanked out the diagram because I want to show you that myself. I'll talk about it more in a minute. But this alteration process is what makes it so difficult to do this. So we did something very new, which was instead of looking at carbonate, we looked at the mineral barite. And barite is a mineral which you might not know very much about, because it's quite unusual. It's barium sulfate. This is what it looks like in an outcrop in southern Africa. This is its chemical formula, barium sulfate. There's no strontium there, is there? But if you know anything about chemistry, you know that barium is in the second column of the periodic table. It's an alkaline earth metal. And immediately above barium in the periodic table, we have strontium. So strontium forms 2+ cations, just like barium does, and has a very similar ionic radius. So barite, when it forms, captures strontium as well into its crystal structure. Barite contains around 1% strontium. And barite is extremely insoluble. It doesn't dissolve in water. if you ever do any chemistry experiments with sulfate, you know that if barium's around, you get to precipitate almost immediately. So you need very low concentrations of barium to precipitate barium. So that means that it's been sitting there in the crust, not doing very much for billions of years. It's been well preserved. And traps these isotopes as well, which we're interested in. So let's discuss the barytes a bit more. Now, barytes is a rare mineral, as I said, and this is another quite complicated diagram, which we'll spend a bit of time talking about. It shows how the composition of the atmosphere has changed through time, specifically atmospheric oxygen. So we're sitting here today, on the left-hand side, we're back in time in this direction. When we go back in time to the beginning of the Phanerozoic, there's a drop in oxygen concentrations. It's the Proterozoic. And then when we go through the Proterozoic, we have another drop in oxygen concentrations when we go into the Archean. So the Archean Earth was oxygen poor, it was anoxic, and this was the point in time when the first microbial biosphere appeared. So these diagrams are studied for all kinds of reasons. The evolution of the atmosphere is linked to the evolution of life. But there's another key thing here, which is the sulfate mineral record. We have lots of sulfate minerals all the way through the Phanerozoic and the Proterozoic, but we don't really find them in the Archean very much, apart from a few isolated localities. And these are all the barytes, which I've just been discussing a moment ago. Now, we make sulfate minerals on the modern Earth by reacting sulfur with oxygen. And if we go back to the last slide, you'll see that sulfate is indeed a molecule made of sulfur and oxygen. So because we have oxygen in the atmosphere, we can make sulfate minerals. But in the Archean, this is very perplexing. It perplexed people for a long time. We produce these barytes, and nobody really knew why they were there or what they were doing. Now, ocean chemistry also changes across Earth's history. Back in the Archean, we had iron-rich oceans. We had oceans in the Proterozoic, which could have been iron or sulfur-rich, and we only had oxygen in the oceans very recently in the Phanerozoic. So I want you to keep this in the back of your mind as we go further. The conditions on the early Earth were very different, not only in terms of the amount of land, but also in what's going on in the atmosphere. So let's go back to our barytes. Let's go back to southern Africa. We worked in this area in the northeast of South Africa, close to the border with Eswatini, which is the country which used to be called Swaziland until not so long ago. And there's a beautiful fragment of early crust there called the Ringstone Belt. And these rocks have ages between about 3.5 and 3.2 billion years. And we find lots of barytes in these rocks. So we can sample barytes at different ages and different metamorphic grades. It's a very nice place to do field work. This is me, standing on one of the outcrops. And I'm now on the opposite side of the valley to where I showed the photograph on the title slide. This is an incredibly steep valley, by the way. And the geology is really weird in the Ringstone Belt. So this valley exists because there's a dike running along it. And this is a Karoo age dike, so it's Permian in age, it's Dolerite, and it's weathered preferentially. That's not what we see normally, is it, on geological fieldwork? Normally dikes form positive topography, but in these Archean greenstone belts, they form steeply negative topography. And that's because the sediments, which are sitting on either side, are highly silicified. They've been silicified because there was a lot of silicon in the oceans on the Earth. It percolated into the rocks and has preserved them. And then the Permian dike, which is not silicified, is weathered out and it's created this steep valley, which you can't cross, by the way. This is so steep, you couldn't get across it. It would take you the whole day to climb down to the base and go up the other side. Plus, the valley is full of nasty snakes. So we don't go down there. The barytes look like this. They're beautiful rocks, actually. On the left-hand side, we have what we call a crystal lawn. So lots of crystals of barite break upwards. They give us a nice way up indicator when we've done field work and we're looking at sedimentology of these systems. And they form little vents. So they're forming around places where fluids are venting on the seafloor. And they quite often contain organic matter as well. And that's something we're also really interested in, because we think these little vent systems are places where microorganisms could have thrived. Here's a map from one of our colleagues in the United States, Don Lowe, who's also studied these systems. So looking at a cross-section now through the rocks. And the dark green stuff is the barite, and it occurs in very close association with silica, with chert. So what we actually had were fractures which formed on the early seafloor, and fluids vented from a depth, probably from some kind of reservoir in the sandstone, and they percolated upwards, driven by a thermal gradient. And the sulfate from the seawater mixed with the barium, which was coming from below, and it made our barite. Now, we've been doing field work in the 21st century, so we use drones these days. These places are often on very steep hillsides, and they're difficult to map. But with drone mapping, we can really reconstruct very nicely these vent systems. And we've done a lot of geochemistry on these rocks as well, and we can see that the barium is definitely coming from below, and sulfate is coming from above. So these two chemical compounds meet, they precipitate, and they form this little barite. And then that captures the strontium from the seawater at the same time. Now, when you think about seafloor vent systems, you often think about modern day, you think about mid-ocean ridges, which are quite high temperature systems. But this is a very low temperature venting system. And we can see that in the geochemistry. We can look at some of the elements that we find in these systems, and they indicate a very low temperature. So here's another cartoon to show what's going on. Here's one of these vents. The barium is coming from below, the sulfate is coming from above. I want to say more about that next. And then we find these beautiful barite domes which form in these systems. And then further away we find that the stuff is reworked into sandstones. That's another key detail I'll talk about in a minute. So let's go back to the field again. This is another place that we worked at in South Africa. This is me with a colleague from the United States. Beautiful place to work. Now, when we look at the rocks under our feet, again, we see that they're weathered, altered. So they're orange. And if you've ever done field work in one of these areas, you know you get covered in orange dust. When we go out in a vehicle, we typically rent a vehicle from the airport when we go to Southern Africa. When we return to the airport, we have to pay lots of money to get everything cleaned professionally because the car fills up with orange dust. When I was in Australia last time, I slept in a hotel in Perth on my way home, and I woke up the next morning after sleeping in my bed, and my bed was completely orange from the dust that came out of my head. And that's from all the iron in the rocks which is weathering out. So one thing we can do is go into mines underground to get fresh samples. This is Desiree, who's my colleague, who was a co-author on the study. She was named on the title slide. She did her PhD with me at Utrecht 10 years ago. She's now an associate professor in Bergen in Norway. So she worked on this project. We could go into mines, but the problem is in a mine you're following the places that the miners went. And these are not necessarily the best places to do geology. So what we've done is we've been involved in some drilling projects, international drilling projects, where we've deliberately gone and looked at fresh rocks to solve scientific problems rather than commercial problems. I was involved in a big project in Pembrokeshire 10 years ago, and there's another one going on right now to collect fresh material to look at early life, questions of the early biosphere, and to look at the early environments, early oceans and atmosphere. It was quite fun doing this project. When we arrived there, we advertised for people to come and work on the drilling rigs. This was the first day that we put an advert out, and lots of people wanted to come and work with us because we were providing employment, of course, in an area where there isn't a lot of employment. And it created a lot of interest in the local town. This is a newspaper article from Barton. The local community were really on board in our project. And Barton is now a UNESCO World Heritage Site, partly thanks to the work that many geologists have been doing there over the last 30 years or so. We collected fresh drill core every day from the sites we were working on. And me with some of my colleagues looking at what came out of the ground at one of these drill sites. We logged the core, measured it, oriented it, and then we had to drive through quite spectacular countryside. Actually, this is the place where I learned how to really drive a car. I have lots of stories about that, I can tell you about it. We drove the core back to Johannesburg. These are two of my PhD students, Alexandra Delich and Alicia Montanaro, who worked in Munster, University of Munster, and we logged the core in detail as it came out of the ground. Now, one of the things that we first measured in these rocks were sulfur isotopes. And you see that my clock is ticking. I'll go as quickly as I can with this. We measured sulfur isotopes in two different ways. We measured delta 34S and delta 33S. And I don't know how familiar you are with sulfur isotopes, but this whole field of study went through a revolution over the last 10 years or so. Because what we do is we measure these two components, and on the Earth they should define a straight line, which is called the mass-dependent fractionation line, and that's defined by this equation here. So the amount of fractionation on the 33 isotope should be about half of what we see on the 34 isotope. If you don't really understand this very well, it doesn't matter. But what we found for these very old rocks is that that relationship doesn't always apply. Quite a few of the samples lie off this line. When we see that, it's called mass-independent fractionation. This was a discovery made by one of my colleagues and close friends, James Macquarie, 15 or 20 years ago, 20 years ago now. And at the beginning, it wasn't very well understood what this represents, but what it means is quite important for interpreting these rocks. So sulfur is produced in volcanoes. It gets carried into the atmosphere as gases, SO2 and H2S. They interact with ultraviolet light, which is shown by this little parameter here, this times constant, times frequency. And it makes all kinds of species in the atmosphere. And this happens today, just like it happened back in the Archean. But the critical difference in the Archean was we didn't have very much oxygen in the atmosphere. So if we have very low partial pressure of oxygen, which is less than 10 to the 5 times the present atmospheric level, this ultraviolet light becomes very strong. And these gases split up into these different components, and they can't mix back with one another. So today we have oxygen in the atmosphere, and it means that all these species get reoxidized and end up looking like this, and all mixes back together, and we don't see anything. But with low concentrations of oxygen, these species actually end up in these minerals, and here's our barite, which is one of these members, and another one is pyrite. And these trap this sulfur out of the atmosphere. So the sulfur is actually coming through the atmosphere to get into the rock. It's not getting into the rock from weathering, as I told you earlier, because we have no oxygen around. So this was the first thing we wanted to study when we looked at these rocks. And we get to work in some really cool labs. This is the Sims lab in Stockholm, where I did quite a lot of work. And I worked in this lab with Martin Whitehouse. It fills a room. It's really impressive when you go there. This is my colleague Martin. And it was actually quite funny looking back on it, because the instrument always used to break down when I went to Stockholm. And I went there 5 times altogether. By the 4th time I went there, Martin said to me, "I'm going to call you, Paul, at the airport, and if the instrument's still working, you can get on the plane. And if it breaks down, you can stay in Holland." So I went to Schiphol Airport in Amsterdam and called Martin, and he said, "It's okay to get on the plane." I flew to Arlanda Airport in Stockholm, which takes about 2 hours. I got off the plane, I turned my phone back on again, and there were 4 messages from Martin. And the instrument had broken down while I was in mid-air flying to Stockholm. So I helped him repair the thing instead of doing my measurements. It's an interesting side story. So we went and measured our barytes. So this parameter here, cat delta 33, is that deviation from that mass-dependent fractionation line that I just showed you. So most modern rocks are 0 on this y-axis. They just fall along this axis. And our barytes fall off that axis, which means that that sulfur has been through the atmosphere. It's interacted with UV light. So that means 2 things. It means our sulfur is coming from seawater. It's very important. It's coming from the surface. It's not coming from above, from some kind of hydrothermal process. And it also confirms that we had low oxygen in the atmosphere. It's a completely different story about that let's go into today. So this was exciting at the time. We published this back in 2012, and we produced a very complicated model that I don't have time to explain, but our model essentially argues that all the variation that we see in the sulfur isotopes is due to bacteria changing our state ratios. So we were also able to argue that early life was present at this time, 3.2 billion years ago, and it was processing the sulfur. And again, that's a complicated story, and I can't explain it all in detail today. And we were excited about that. We published it in this paper. But we found something we couldn't explain, and that was a time progression in the data. So the older barite deposits had a different mesotypic composition to the younger. We couldn't explain it. We wrote it in our paper, and we forgot about it. And then about 5 years later, Deja came along to me and said, why don't we go and measure strontium isotopes in barytes? Because nobody's done it since the 1970s. And back then, the techniques that we had weren't so great. And it might tell us something about what was happening tectonically. So we thought about it a bit, and then we looked into all the problems I've been explaining today. And we thought, yeah, this is a good idea. And this is a nice example of how sometimes you stumble upon problems that you don't expect in science. So originally, when we studied these things, we were looking at early life, early atmospheres, and so on. And we actually stumbled into this problem of early crystal emergence almost by accident. So anyway, we went and did the measurements. We drilled the samples. There's different types of barite, as I mentioned earlier. There's granular barites and there's bladed barites. So they come from different parts of these vent systems. And we measured the strontium isotope values. And we plotted them. And we found something really remarkable. The data came back out of the lab. We plotted the age against strontium isotope values. And we saw that you could join the base of the variation in each deposit by a straight line. Now we saw that back at the beginning of the talk today. A lot of the variation that we see in these lines had to be explained. So we did that by looking at the types of barite that we have in these systems. And we found a clear difference between the granular barites and the bladed barite. And the bladed barite, which forms closest to the axis of these vent systems, actually has the lowest strontium isotope ratios. And the granular stuff, which is very fine grains, and where groundwater can percolate through today, that has higher values. So that's actually a little bit weathered and it deviates from the trend. We measured a lot of other isotopes as well, as geochemists like to do. We measured oxygen isotopes in the barite because the barite is made from oxygen as well as sulfur and strontium. And people have estimated what seawater would look like back in the Archean. And we found that all of our values sort of fall within that seawater field. So it didn't help us a lot, but it's consistent with seawater. And we did the same thing with sulfur isotopes. But we went back to this unusual trend that we couldn't explain in 2012 in our multiple sulfur isotopes here. We plotted the strontium isotopes against the sulfur isotopes, and we found a perfect straight line in the bladed barites. Granular barites fall off because they've been affected by weathering, actually. So even though barites is very insoluble, it can still be affected. But blades, these nice pristine blades, weren't affected. And this straight line actually is our seawater evolution curves. This is older seawater, slightly younger again. And these barytes actually now come from lots of different locations. We didn't only look at barite in South Africa, but also from India and Australia. Of course, these places could have been connected to one another in the Archean. They cover lots of different metamorphic grades and geological environmental deposition. So I actually think we solved this global problem, which I was talking about earlier as well. So, okay, what we've done here is we've taken these bladed barytes. You can draw a straight line through them, and then you can see where it intersects the curve for the mantle. Now, there's lots of different estimates from what was going on in the mantle. This is a primitive mantle curve. These are different depleted mantle curves. I can explain that with you at length if you're interested. And this is our data. And what we realized was that our barite doesn't necessarily equal seawater. We had to calculate what seawater would be from the barite data. So we ran a little numerical model. We calculated the conditions under which barite could precipitate in a vent system. And then we calculated the uppermost and lowermost values that would be in equilibrium with our barite under likely scenarios. So we actually made a band of compositions for the barite, and that intersects a band of compositions for the mantle. And if you do that, you get this area, which is this sort of orange box, which is around 3.7 billion years ago, plus or minus about 0.15. It's a beautiful straight line. It intersects the mantle curve very nicely. What it shows us is that this is the point where land first appeared above sea level. It starts weathering. It starts to change seawater chemistry. We don't have any rocks from that age to test it. The oldest rocks we have are from here. So if our projection is correct, this is the age of land first appeared. Nobody had been able to do this before. This is all of the data again of the carbonate record, all that's scattered. This is our data. So you can see it's much more tightly constrained, and it allows us to calculate this projection, this regression, if you like, to get this age. And we're really excited about this, and we just published it last week, or a week before last, as Harry mentioned. And calculate this age for the emergence crust. We can also do some calculations to estimate how much crust had emerged at these times for when we actually have the rocks. So our oldest rocks are here, 3.5 billion years ago. And this red line here is a line assuming that weathering rates in the Archean were the same as they are today. And that's an unknown. We don't know if weathering was more intense back then, or less intense. But if it was the same, then we would get somewhere between 7% and 12% of the Earth covered by crust in the Paleoarchean. That's a lot. So 7% of the Earth is equivalent to modern-day Europe. 12% is equivalent to modern-day South America. But if we have hotter conditions on the early Earth with more weathering, then we'd have one of these curves. If we had colder conditions, we'd have this one. So we can't, unfortunately, conclusively say exactly how much of that globe was filled with land at the time. We can just give ranges. But it's a lot, so there's a lot more than people previously thought. We've effectively pushed back the age for the emergence of crust by 500 million to 1 billion years, depending upon whose estimate you want to take. And again, why does this matter? Well, it's actually quite a nice result, because the first rocks we find in the geological record have these kind of ages. So the first extensive rocks that we can find today are around 3.5 billion years. So they've been preserved. So that means we must have had continental crust since that time. And the first life that we find in the geological record is also around 3.5 billion years ago. So that fits nicely with this idea about delivering nutrients to the ocean at that time. So this was our conclusion. There was an Archean landmass, and it was, the modern day value is around 27% of the Earth's surface is covered with land today. So 7 to 12% is actually a lot. Yeah, quite a significant amount of land around. And that brings me to the end of my talk. So was there an Archean landmass? Yes. If we're correct, then carbon dioxide could be drawn down from the atmosphere effectively by weathering, and that could begin to modulate climate in the way that we see today. Nutrient cycling kicked in, life appeared, habitats became more diverse. So this was the point at which the Earth started to look like the modern Earth for the first time. And on the right-hand side here, we have a cartoon from NASA, which was made in about the year 2002 by a NASA artist, where they drew what they thought the Earth would look like 3.5 billion years ago. It shows volcanoes, it shows land, and it shows hot springs, like a barite-forming environment, oceans, seawater, and it shows these microbial mats, which were the first life, the first microorganisms, bacteria thriving in these environments. Actually, the results of our work is to show that this is probably a very accurate estimate of what the early Earth would look like. So, thank you for listening, and it was quite a long talk. I'd like to take some questions. Just finish with a couple of photographs from South Africa. At the bottom here, we have granite. So this is in the Western Cape, and these rocks are continuing to weather today. So we're still putting rubidium and strontium into the oceans today. This process continues. Of course, we've known about that for a long time. We've just looked at that in a very ancient environment, which might have looked a little bit like the middle of this beach here. We've had lots of quartz, no obvious life. This place called the Dead Road in the Western Cape as well. And, if you don't take anything else out of my talk today, I hope you can appreciate that South Africa is a beautiful country, and please go there if you ever get the chance. Thank you.
Thank you very much, Paul, for a very interesting and insightful talk. And I'm sure you all have questions now to ask. You might not be entirely convinced by some of the results. You might want to challenge Paul. His interpretation may not be part of it. That's why I'm just going to open the floor for any questions you might have. And if you feel uncomfortable perhaps in asking in English and you'd like a little assistance, I'm right here for you to translate. Okay. Thank you very much for once again. Over to you. Yep.
First of all, I have to say that it was very interesting, this presentation. I feel like it showed me like a new point of view of how to see how plant works and what can happen. That's why I have to, I would say, kind of weird question to say the least. Like I feel like someone would say that they may be absurd or ludicrous, but I'm willing to ask. First of all, about the whole idea, actually, no. First of all, I have to say that I learned from some subjects that the charge of our magnetic field, like the North Pole, can change as far as if it's positive or negative throughout the years because of other reasons for many subjects. But what I haven't, what I want to ask is that is there a possibility for the charge to change as far as intensity? I mean, the gravity to increase or decrease, because from what I have seen so far from other, like, from usually stuff, like I found there is a diamond created in space, which is far harder than the diamond in here because of higher pressure and temperature. And I thought that gravity is a very important factor as far as what makes such scenario happen. Like, I mean, to be stronger or to change the basic effects, and at the same time, it's the same mineral. or in Mars, there was like a mineral cave, it was looks like a flower. I'm pretty sure there are some in here. That's why I'm curious, like, can we like see that happening from that research? At least that's the question that I have as far as that. And also about the Percy crust. Is it possible to find such examples in other rocks, as I say, in sedimentary rock, not necessarily in igneous or Percy? I feel like it could be a possibility because Percy may break, may be broken down the mantle, but can always reappear like that. I feel like it's a possibility as far as what I've seen so far. I'm sorry for the I'm a little bit nervous, I don't like
That's okay, no problem at all. So you asked several things, and some really good points. So you asked about the magnetic field. So people have been looking at the magnetic field back through time. And we do know that the magnetic field was weaker in the Archean. We know that for sure. There was a magnetic field. People have tried to estimate the magnetic field intensity in the Archean, and it seems to be much weaker. So that has major consequences for life on Earth, because of course the magnetic field protects us from solar radiation, or solar particles deflecting. So that's one of the reasons why we have an atmosphere. Higher UV intensity was not the only problem for early life, but also particles, some solar particles impinging on the surface. So it's very good to ask those questions as well. But we do think there was a magnetic field at this time.
Yes, what was Zircon, as you said, it's a very hard, hard rock to break from weathering. I thought to myself, maybe back in the day it was made different because there was a different conditions. Because when I'm pretty sure that gravity also affects how the weathering works. Like maybe back in the day it wasn't so hard, or maybe it was worse. I'm not so sure about that. Like I haven't done research or anything. I'm just like hypothesizing, like could have been made completely different, like there's some sort of compounds so far, or maybe they changed from other resources. Like that's probably this question.
Yeah, you're asking about gravitational forces as well. Well, of course, this largely relates to the mass of the Earth. You have local changes in gravitation due to density differences, and of course, these are minor. So that's not a major issue concerning what I've been talking about today. So the gravitational pull of the Earth would have been pretty much what it is now, because the mass of the Earth, well, it's actually slightly increased, but not a lot. It's slightly increased from all the infall of material from space over time. It's very minor. Then you, the last part of your question was? It was
because we, as you said in the beginning, there are a lot of the crust was first, right?
Yeah, that's
right. Is it possible to find that as an example in igneous rock, not only on magmatic rocks, but also sedimentary or transformer rocks, because yes, the material may have broken down, but it can also reappear in other ways.
Yeah, it's a very good question. Yeah, there's lots of different ways to calculate when the first crystal appeared from sea level. I didn't want to show all of this data today, but this is a horribly messy diagram. I apologize for that. These are our data on the top left-hand panel. But here are some of the other geochemical parameters that are used: titanium isotopes, the rock record itself, the extent of protonic rocks, hafnium isotopes and zircons, element ratios like nickel, cobalt, and chromium, zinc ratios in sediments, zinc isotopes in sediments, oxygen isotopes in sedimentary rocks, and all of these have been used to create reconstructions for how the crust appeared through time. And what you'll see from all of these constructions is that none of them have sufficient data and are sufficiently clear to be able to draw regression lines like we did by rubidium strontium data. So one of the great things of looking at the rubidium strontium system is we understand it really well. It's very well pinned down because we've been studying it for 60 years. it's great to look at titanium isotopes, for example. That's this parameter here. And you can see some clear differences at different ages. But there's a new isotope system that we don't understand too well. We just don't have enough data. So there's lots of ways to do this. But the way we've tried to do it here is it relies on decades of background work actually to make it work. So I think you make a good point. Those kind of things as well. Yeah.
While we are talking about pyrite and barite, and a few slides ago, we talked about sensitive crystals, because pyrite and barite is harder but not sensitive crystals.
So I'm not sure I fully understood your question, but why are we talking about barite?
Yes, and a few slides ago, we talked about sensitive crystals.
Oh, yeah, sorry, maybe that's a language thing. So I talked about the sensitivity. Yeah, exactly.
Is it accurate tracer of crystals? Growth should be sensitive.
Yeah, what I mean here by sensitive is it should record the process that you're interested in a very sensitive way, so in a fine scale way. So often when we're looking at processes in geological history, we have to do that indirectly, right? So if you want to measure temperature back through time, you have to use something in a rock that records temperature. Now the way that chemical change records the process is what I mean by sensitivity. So if it's high sensitive, it means that your chemical indicator is very closely linked to your original parameter. A lot of geochemists use the word proxy. You may be familiar with that, maybe you've heard that. What proxy means is that you have an indirect way to measure what you want to measure. So, we can't just go and measure how much crust there is through time with a tape measure. So you don't have a time machine. You can't measure how much oxygen there is in the atmosphere through time because it's not trapped anywhere, and you can't measure that. And in exactly the same way, all these parameters then have to be closely linked to the original. Hopefully that answers your question.
Yes.
You're exactly right. Barite is really insoluble, so as a material, sensitivity is very different.
Okay, thank you.
There was a diagram about Strontium seawater in the beginning, I think 4 or 5 slides. Yeah. And there was a spike, this spike is very recent.
Yeah, this is related to continent building cycles. So when we have more continental crust that can be readily weathered into the ocean, we will see more Strontium-87 in seawater. And the sink for strontium is subducted sediment, which can be carried back into the mantle again. That's where you really sink to get it out of the system. But it's input from exposed crust. So the rate at which we see changes is related to how much material is exposed at any one time, which is related to tectonic cycles. It's a very short answer, because this is actually quite complex.
Well, thank you for your great presentation. You know that high impact work attracts much attention, and then you have more uncertainties and more questions to answer. So, based on that, and because there are much uncertainty in Habian geodynamics, so we talk about the stagnant lead cover of the primitive Earth, and then we have the initiation of plate tectonics. So we place it in 4.4 billion, and then we put it to 3.8. Different techniques and measurements with hafnium, strontium, and all these techniques.
that's a really good question.
Because I thought emergence it would be initiated from something. Is it subduction related? Is it just the regional uplift or mantle blooming? I don't know.
This is not directly about plate tectonics. What we've tracked here is how much crust you have above sea level, calcium crust you have above sea level. It's not exactly the same question as when did plate tectonics appear. Now, the easiest way to make calcium crust is plate tectonics, but you can make calcium crust in a stagnant with tectonic environment, which is the alternative. So, many people think that we didn't have plate tectonics before 2.2 billion years ago, for example. Different people have different estimates, but there's somewhat of a consensus. The modern style plate tectonics started around 3.2, and it wasn't a step function like you see with the oxygenation of the atmosphere. Plate tectonics appeared gradually over time. And there's all kinds of pieces of evidence like the blue schist record, which we're talking about. We don't see blue schist until the Neo-Proterozoics, and very, very young. And there's lots of discussions and arguments about why that is. So our data doesn't argue for or against plate tectonics. It argues simply for the occurrence of weathering of exposed crust.
Yes, but in order to have healthy exposed crust, especially of this composition, you mean that like evidence for plate tectonic initiation was PTGs, differentiation of mantle magma and all this. Okay, and the second big question is how sure all these ratios of Strontium is not altered by bombardment? You know, we're discussing again also about the bombardment of carbonate on dryers, and maybe this can change the ratio of Strontium or hafnium or resetting of rates.
The later heavy bombardment, would that change the
That is how better, I don't know how we call it, we can buy it physically.
It wouldn't change it if you were bombarding the Earth with material from the solar system. Because that all formed at the same time. So the astronomic clock started at the same time for everything in our solar system. If you bring in material from outside the solar system during the late bombardment, then it can mess things up. Yeah. But the material which came in at that time was derived from the same nucleus synthesis event that created our solar system.
I mean it in a way that this bombardment, we calculate the crustal growth, about 8 kilometers, something like that.
Yeah.
So this should be emerging from this.
Oh, it's a physical process. Yeah. Not as an astronomic process. Yeah, of course, the late bombardment would be catastrophic. If it's real, of course. There's recent data from the moon, from the Argon data that's been produced in the last few years, which suggests that perhaps the late bombardment didn't happen at all. If it was real, it would have been catastrophic for the Earth crust. And it would undoubtedly have broken the crust up and might have accelerated recycling into the mantle. But of course, that happens before our record starts. Maybe our record starts because it is somehow linked to the late bombardment, but we can't say anything about that really. We can only speculate with our data. Does that answer your question?
There's no. Thanks, Paul. Yes, thank you very much for having us both in time and in the continents. I like South Africa, particularly South much. They have more vineyards than the area you walk, okay? And I will follow it with a little of ties, and I will ask you a question. I didn't really follow it with the issue with sulfur. So I see, as already didn't make it catch exactly how the connection goes. So sulfur was an assumption, or it was real data, that you had sulfur from photocatalysis. That is an assumption immediately that there was lag. So that was an assumption that you followed into your model, or the data pointed that there was already melting out of the sea. So this means that factors such as chronometry, there is a lag. How this can affect your, or already something that is concluding and it is strengthening your interpretation for the 3.5. That's what.
Yeah, that's a very good question. I didn't really have time to explain the sulfur dating properly. I went through that very quickly. I did that to show you that we started working with these rocks for a different reason. The sulfur isotope work is completely decoupled from the strontium isotope work, with the exception of this one parameter, this capital 33S parameter, that's the mass independent fractionation, which changes through time, just like the strontium isotope does, it changes through time. And our conclusion is that the oceans are changing through time. It's the composition of seawater changes for both the sulfur isotopes and the strontium isotopes together. And there's some good reasons why that might be. So strontium isotopes change because of weathering, the sulfur isotopes can too. And that's because the sulfur is all coming through the atmosphere from photolysis. We know that because of this isotope anomaly. And there's two types of sulfur come out of the atmosphere. One is sulfate, which is soluble in seawater, which makes barite. But the other type is elemental sulfur, and that's insoluble. And that can land into the oceans, and it can arrive on land as well. It can be delivered to early land. And if it's delivered to early land, it's susceptible to weathering. It can be carried back into the oceans by weathering. And elemental sulfur, there's an additional complication. It gets broken down most readily by bacteria to get it into the minerals that we see. So the bacteria is sitting in the middle of that process as well. But we think that this seawater evolution curve is consistent with weathering carrying sulfur from land to ocean, as well as strontium from land to ocean. But we didn't put that into our paper just now. This is too much detail, there's too much information for a short paper. But we're working on that right now, trying to explain that better.
Yeah, Paul, thanks very much for your interesting talk. Just a quick question. It is well known that the strontium and the rubidium are quite mobile as elements. And at one point in your talk, you mentioned that the barytes were formed under low temperature conditions. And you were convinced that due to the rare earth element patterns. Was that convincing enough data for you to spot this? Because if there was a high temperature event, maybe that would have changed. Because we're talking about many, many millions of years. Even one process that would seem to us as a moment through this time could have done some damage in the output of data.
It's a really good question. Yeah. So one of the reasons why these things weren't studied in a lot of detail before is because we didn't really know how these barytes formed. So it's only recently that a lot of work has been done to try and figure out how these vent systems work by Don Lowe and some people. And a lot of people who work on the early Earth try to avoid anything that's been formed at high temperature because that resets our geochemical traces. And it means we're not looking at the surface processes or low temperature processes we want to study. So this is a major concern. Now, one of the great things about the barytes is it contains about 1.5% strontium. So it's really a lot of strontium. So one of the first things we did was do some calculations to work out how easily you could reset the strontium isotope ratio by antisemitism, for example, by metamorphism. And we calculated that was unrealistic, that you'd have to have very high concentrations of strontium to reset the baryte. Also coupled with the fact that the baryte is very insoluble, it's very difficult to change that. We actually put some of those calculations into the supplements of our paper that we just published. I can show you some detailed figures as well if you're interested to show how that worked. So that was one point. The temperature of the vent systems, it would be really nice if we had a way to measure that, but we don't. So what we did was we looked at rare earth elements in the cherts, which are associated with the barite. The cherts and the barite are interbedded, they cross-cut one another, they have cross-cutting relationships, so we know that it formed together. And in the cherts, we see europium anomalies, which are small. And the magnitude of the europium anomaly correlates with the temperature of hydrothermal alteration in a very rough way. But it's not an accurate proxy. We can't get an exact temperature. But based on the europium anomalies and shapes of the rare earth element patterns, also what yttrium and holmium are doing, we can argue that the temperature is most likely less than 150 degrees to 200 degrees, that kind of range. And that's as good as we can do. Okay.
Well, thank you very much for everyone. And only an observation, a thought of mine. Taking into consideration all the data that we're currently collecting from us, is there a possibility of comparing the data, or in the future to compare your data? I mean, we have barite and celestine in mass as well. So is there a possibility of in the future to make comparison?
That's a good question, which I've never thought about, to be honest. So on Mars, you also have an atmospheric sulfur cycle. We know that from the Martian meteorite records. So we know we find this massive Martian energy. We didn't have photonics on Mars, so that's it. But we probably had oceans and rivers. Make estimates of what was going on back slightly older than this period of time, I guess, in the Narnia. So if we could get hold of rocks from Mars and we could estimate what was going on in, I guess, tectonic events where in terms of crystal growth, we can link that back into models we have from the terrestrial record quite well. We could make measurements on the barite, and maybe we could see what was going on Mars a bit more clearly. Interesting idea. Never thought about it. Do we know how? Yeah, sorry. We should talk about it. Yeah.
There was a diagram in one of your final slides that showed the quantity of the isotopes of Strontium throughout time, and there were two lines that showed the liquidity value. This one. And you said that the square created in this diagram shows that the first continental crust emerged in that time period. How long did you come to this conclusion? That's my question.
So what we're looking at is this box essentially here, where this intersection, or these intersections roughly define a field of age here when the emerged seawater, the seawater from the emerged crust and the Earth's mantles, this is really like the whole curve, intersect with one another. So if nothing was happening on Earth, as I showed back at the beginning, you just have a straight line here through like this. And as I mentioned right at the very beginning, if we take out something that has high rubidium, then that material is going to evolve here, and what's left behind in the mantle is going to go down. So what we're trying to do is figure out how our steeper curve interacts or intersects with the line for the evolution of the whole Earth. And that's what we've shown here. And there's different estimates for how the mantle would evolve through time, and that's why we've got different lines, different black lines in this diagram. We get slightly different estimates for our seawater composition based upon how the strontium was exchanging between seawater and the barytes in our hydrothermal system. And we had to explain that in the model. So I agree, it's not very clear to see that on this figure, but the uncertainties lie between all of these dotted and straight lines you see in this diagram. So this is one extreme of seawater. This is another extreme of seawater. This is as far back as we can go in time with the rocks. So then we extrapolated, that's why we should have dotted the lines. This is one estimate for the mantle, this is another estimate, and another estimate again for the mantle, depending upon how depleted it is, which is also linked to how you extract continental crust, which is shown at the top there. So this is not the period in time when the first crust is extracted from the mantle. That's something different. We should be much older, not to the right-hand side. This is the period in time when weathering affects the ocean for the first time. I hope you can follow this. I'm not confusing you.
Kind of.
I'm kind of confusing you.
No, I kind of.
You kind of follow me. I'm very happy to discuss it in more detail and go a bit more slowly after the talk. And anybody else wants to ask about this as well. So, two different things shown on the same diagram.
Okay. Well, Mark, you highlighted the importance of the Landmass emergence concerning the carbon cycle and the change in the ocean chemistry. Since climate change is a hot topic these days, do you plan to use these results in order to see how temperature change from these times recently?
That's a great question. One of the problems is we don't really know what was in the atmosphere back in the Mαρτίου. That's a huge open question, waiting for somebody to find a solution. So for a long time, it's been argued that there was lots of carbon dioxide in the atmosphere, very high partial pressure carbon dioxide. We need some kind of greenhouse gas so that we can have liquid water on the Earth's surface. We know we have liquid water because of the oxygen isotope data from the zircons, but also from the fact that we had sediments at this stage. We find sedimentary rocks going back to 3.8 billion years ago, we all by modern sediments. So the water was flowing. So that limits our temperature range from 0 to 100 degrees. So based on that and how strong we think the sun was at that time, because the sun was actually weaker at this time as well, it's an additional complication. You can make models what you think was in the atmosphere. We've got no direct way to measure it. If it was carbon dioxide that was the greenhouse gas, then yes, this process is really important for regulating climate back then. But another possibility is that we have lots of methane in the atmosphere, and it was methane that was creating the greenhouse. And in that case, it's still important because the methane would have been produced partially probably by microorganisms. And microorganisms are linked to weathering, as I showed you today, and different habitats which were possible. You can also make methane abartically as well during some antimonization reactions. So there's just too many uncertainties actually. It's a very, very good point, but I don't think we're going to get there in the near future.
And my second, more philosophical, let's say, question is, have you studied also the phosphorus in this whole procedure and try to do some correlations with the emergence of life in this planet?
Studied what?
Sorry?
Phosphorus. Phosphorus. Oh, phosphorus, yeah. Yeah, no, we haven't studied phosphorus. No, we've been following closely what other people have been saying. So there's been quite a lot of attention given to phosphorus cycling. There's a lot of uncertainties there as well. We don't know what compounds phosphorus would have existed in the oceans. They could be quite different to what we see today. A lot of phosphorus that what I should say is the phosphorus that we find today in ancient rocks is exclusively an apatite. We don't have any other information about where phosphorus would be or what it was doing.
I'm asking because recently we find a lot of phosphites within the mantle rocks and ophiolites, and I was trying to see if there is a connection between these processes because I guess that these phosphites are probably related with serpentinization. So again, circulation of probably sedimentary water with these adduction zones, and maybe there could be a correlation there.
Yeah, there's a lot to learn still about the early phosphorus cycle. So this is an interesting angle. We don't really know how the phosphorus was mobilized and how it became bioavailable. And there's been lots of work done on origin of life. It's been suggested that life could have originated in seafloor hydrothermal vent systems. But one massive problem with that hypothesis is how you get phosphorus down there and how it can be bioavailable. Nitrogen and sulfur are also a problem in these vent systems. Yeah, very good point. Thank you.
Can I have the last question? Sure. Well, I know we've talked about this before a lot, obviously, but because I remain a little bit convinced about the whole sulfur cycle back in those times. I mean, how do you end up with sulfate to drive the barite deposition in an anoxic atmosphere or system? And if I may add another point, I mean, we are dealing with an ocean-dominated planet at the time. Do you find barite from submarine venting or associated with submarine venting that doesn't record new?
Yeah, that's a good question. We haven't found it. Yeah, you would expect to find barite in a submarine hydrothermal vent environment.
So you did have BMS deposit like that. You did have
well, actually, we looked at barite that's in the same formation as where we have a VMS deposit, but the VMS deposit doesn't have barite in it. So that's very curious. This has puzzled me as well. Why can't we find hydrothermal barite in this time? I haven't found it yet. So this is a cartoon relating to what you were just discussing. We can produce sulfates in the atmosphere as a species through this atmospheric photolysis route.
So UV, yeah.
It's UV related. So we take SO2 from our volcanic outgassing and we break it down in the presence of ultraviolet light. So this has been done experimentally. But we also know this happens today. So on Modern Earth, we found these anomalies in ice cores. Not we, but other people have found these anomalies in ice cores in the Antarctic. But it's not significant today because we have oxygen in the atmosphere, which reoxidizes all these reduced species and it just mixes everything back together again. So it doesn't get preserved. It just gets instantaneously preserved and it gets lost very quickly. So this is a very valid mechanism for producing sulfate. But we do need a way to get our SO2 into the atmosphere. And it's very helpful if you have a large-scale subaerial eruption. So what I showed you here, actually today, is the appearance of the first large-scale landmasses on the Earth's surface, 7 to 12% of the Earth's surface. We, of course, cannot rule out at all that there was some land prior to 3.7 even. Because we could have still had ocean islands. Let's, for the sake of argument, say that we had plumes throughout the entirety of Earth's history. So if we also have plumes in the Hadean, then you would have ocean islands like Hawaii today popping up out of the ocean. So they could have, I don't think we can say that the Earth was a 100% water world ever. There was probably always some of the ocean islands. So if you need some land for any kind of process related to the origin of life or for getting gases into the atmosphere, sure, it would be possible. It would have been mafic in composition. That's why we don't see any strontium isotope record. prior to 3.7, so it's probably mainly make it first. And there's another issue with the rubidium strontium system as well, which is you need time to grow an isotopic strontium-87. So our system is only sensitive to within the timescales of rubidium to strontium decay. So you can levy that criticism against us if you want, because you go further back in time, there wouldn't have been enough time to grow this stuff in. Nobody's
So in that case, when you have the first emergence of land, you're supposed to have also shallow areas, like some small lakes, to have evaporative deposition. And then you would have this anoxic, sometimes environment with sulfide reduction of bacteria that can cause this inorganic material in this one. This can change your sulfur content, or is the emergence of the early organic material of life.
So, yeah, the metabolisms which process sulfur would definitely change over time. So sulfate was extremely scarce in the Emergence. Concentrations were less than about 8 micromolar compared to 28 millimolar today. So really low concentrations of sulfate. You can be quite confident about that based upon what we see in sedimentary rocks from the Archaea. There was lots of elemental sulfur around from this pathway, which was shown behind me. And elemental sulfur can be processed by microorganisms. It's a metabolism called elemental sulfur disproportionation, which microbes can get energy from. So that would have certainly played a role. Sulfide would have been oxidized as well, sulfide oxidation, as well as sulfide around. So the whole sulfur cycle was very different. And it interacts with life in a very different way. So today, sulfate reduction is the dominant sulfur metabolism that we have, which oxidizes organic matter. But that wouldn't have been the case. Sulfate reduction was possible in places where you had elevated sulfur. And those would be local environments. And we did find those. We found those as old as 3.5 billion years ago. That's the earlier work that we did with the data in PhD 10 years ago. And other people have found this as well. And they were localized environments. Does that answer your question?
Yeah.
I think that's it. Thank you very, very much once again. Fantastic document.
Thank you. I really appreciate your questions. There's some very good questions today. I really like that. This morning I was talking to Harry and I said to him, how much geochemistry does everybody know here? And I was a little bit concerned that I was going to show too much geochemistry, but from the quality of your questions, you guys are very up to speed about these things. I'm impressed. Thank you. Great questions. Thank you, Paul. Hope you come back.
Right. Thanks very much, everybody.